Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the Linear Algebra Guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Over here, we have a system of three linear equations. The reason that this system is linear is because the highest exponent on all of these variables is 1. If, for example, I were to introduce an exponent on 2 to any of these equations, then this system would no longer be linear. Now, to solve this system, we need to apply a method called Gaussian Elimination. But before doing that, we need to learn how to represent this system of equations in terms of a matrix. Here, this coefficient matrix would have one column for each variable, and the entries in these columns would be the coefficients of these variables. So the first column would contain entries that represent the coefficients of the variable x. So in this case, 2, -2, and 4. The second column would contain entries that represent the coefficients of the variable y. So 1, 2, and 1. Lastly, the third column would contain entries that represent the coefficients of the variable z. So 2, -1, and 2. In order to represent this full system of equations, we need to add on a column that represents what each of these equations are equal to. To show that this isn't part of our original coefficient matrix and we're adding this column on, we create a dotted line that represents the separation between the coefficient matrix and the values that each of these equations are equal to. Here, these values would be -2, -5, and 0. The first row would have -2, since 2x plus 1y plus 2z is equal to -2. The second row would have -5, because -2x plus 2y minus z is equal to -5. The third row would have 0, because 4x plus 1y plus 2z is equal to 0. When we solve this system, we will obtain one of three cases. The first case is that this system would have one solution. Here, there would be one value that for each of these variables that satisfies each and every one of these equations. For example, and this is just an example, this is probably not the solution to this system of linear equations, we could have the values x is equal to 1, y is equal to 2, and z is equal to 3. If we were to substitute 1, 2, and 3 in place of x, y, and z in all of these equations, we would obtain all of these values, and this would be the solution to this system of equations. The second case is that we could have no solution to this system of equations. If we have no solution, there's no set of values for these variables that satisfy all three of these equations. The third case is that we could have infinite solutions. Here, there are infinite sets of values that satisfy all of these equations. To tell which of the cases we're dealing with and to obtain the one solution or infinite solutions, we need to apply a method called Gaussian elimination.